Hello, everyone. My name is Flora, and I am a research engineer at Google DeepMind. So as many of you might have known, Google DeepMind has been working on applying AI to a lot of various science directions. And one prominent example of that was AlphaFold. And today we're presenting one of our more recent work, also in the science sphere, which is applying AI to power global weather forecast. So the weather forecasting system has been one of the most greatest and long-standing challenge for the humankind. Every day, every individual, we need to rely on accurate weather forecasts to make decisions. From smaller things like if you need to take a rain jacket with you today, to larger things like if you need to actually evacuate from a very dangerous storm. So beyond consumer weather forecasting, better weather models actually can impact a lot of downstream industries. And this is also why I'm standing here today to introduce you to some of our latest results. So with accurate weather forecasting, we can better predict the supply for wind farms. We can better optimize for the control for commercial cooling towers. And we can also help farmers with their plans. And we can even help the governments to predict natural disasters like wildfires and floods. So traditionally, the challenge of weather forecasting has been tackled using numerical weather prediction systems. So these numerical weather systems, they're trying to simulate the atmosphere using physics models. For example, it's trying to tell if the humidity in the atmosphere is going to impact any rainfall, or trying to see if the solar radiation on top of the atmosphere can impact the temperature. So because of all the complexity in these physics systems, we end up with a bunch of really hard to solve partial differential equations that we don't really have an analytical solution for. So how do we find solution for them? Is that we basically run these equations on supercomputers and trying to find approximate solutions to them. A prominent example of such numerical weather prediction system is the HRES model released by ECMWF. So HRES stands for High Resolution, and ECMWF stands for the European Center for Medium Range Weather Forecast. So this HRES model is one of the operational models in the world where if you are working with weather data or weather agencies, they are mostly getting their raw data from this agency. And yeah, that's why we are using this model as our baseline too. So this model is very slow. It runs only 4 times a day and has to run on a supercomputer with thousands of nodes. And another major drawback from this model is that it cannot learn from historical data. So there naturally comes our solution, which is to use machine learning to learn from this historical data. So just to give you a sense of how much historical data we have, so a single forecast run can generate 35 gigabytes of output. As a comparison, if you're looking at some modern video generation models like image and video, like its output size is only 1.4 gigabytes, but ours is 35 gigabytes for one forecast run, and we have 40 years of such forecast data. So that's why it's really efficient to use a graph neural network to learn from these past 40 years of historical data. And our machine learning model is very fast. It can run on a single cloud TPU v4 device instead of thousands of nodes on a supercomputer. And to generate this 35 gigabytes of output, it takes us less than 1 minute to generate all this data. And of course, our model can also run on GPU and CPUs. It's just slower in terms of speed. So our model has achieved SOTA performance on medium range global weather forecasting. And by medium range, we mean from 6 hours up to 10 days at a 6-hour step. And one of the most important milestones that is achieved by this model is that it is faster and more accurate than ECMWF's HRES model. And we call our model GraphCast. Cool, so next up, we'll be talking a bit more about the GraphCast model architecture and how we train this model. We'll also show some evaluation results comparing to ECMWF's HRES. And lastly, we'll talk about some downstream applications. Cool, so now let's dive a bit more deeper into the model architecture. So the GraphCast model takes a 3D global weather state as input. So why is it a 3D weather state? It's because we not only models the surface variables here, but also we need to take into account all of the atmospheric variables that's like up in the air, because the weather is not just something that's happening on the ground level. We take all these data and try to segment them into smaller cubes. So on the surface level, these are lat-long grids, and also because the atmosphere is so high, we segment them into different pressure levels. So this is basically a globe that is consisted of several, actually millions of these smaller cubes. And we feed this 3D global weather state into our model, and the model will be able to predict the next weather state, that is 6 hours later. And to get a forecast for up to 10 days, the way we do it is just we roll out the model iteratively in an autoregressive way. Basically, we feed the output of the model back into the model again as an input. So just like a language model. And we autoregressively roll out this model every 6 hours up to 10 days. So what is inside this GraphCast model? So there are actually 3 different components. One is the encoder, and another is processor, and there's a decoder. So the encoder is responsible for mapping all these smaller lat-long grids onto some nodes in a mesh network. So this mesh network is actually the bulk of this graph neural network. And for those of you who are not familiar with a graph neural network, I prepared a 1-minute crash course on what is graph neural network with an analogy to transformers. So transformer is actually a special case of graph neural network. And here I'm showing a graph of this classical attention mechanism. And as you can see here, this attention mechanism is actually forming all these edges that are trying to connect all these nodes together. So what we are getting here is actually just a fully connected graph. So that is why transformer is actually a special case for graph neural network. And the difference is that the transformer, the way that it learns is by aggregating information from neighbors, and the way it aggregates information is through attention, which is essentially doing some weighted summarization. And instead, for a graph neural network, we call this training procedure message passing, which essentially is similar to learning these attention weights in transformers. So basically, this is how graph neural network works. So now there comes a natural question, why don't we use transformers now? The reason is that transformers has a quadratic memory cost because we have this fully connected graph. So when we are doing the attention mechanism, we need to do a lot of all-to-all matrix multiplication that is giving us a quadratic memory cost. So it does not scale very well if the input length is very long. And remember, in our case, we have more than 1 million grid points. So it's just impossible for this model to process so much input. So it's more natural to just use a graph neural network in this case. Cool, so coming back to this model architecture graph, we just talked about the encoder is responsible for mapping the lat-long grids onto a node inside this graph neural network. And this graph neural network, it actually looks like this. So it's 7 different mesh networks at different resolutions stacked together and connected together. And the reason we have these 7 different resolutions is that it can model both coerced relationships and also more fine-grained relationships. And this brings us back to some concepts similar in transformer, that we want to model relationships that are shorter term and also longer term. So this processor is responsible for the message passing, which is the learning inside this stacked mesh network. And finally, we have this decoder where we are mapping all the relevant nodes on this mesh network back onto this lat-long grid, which is back to the weather state. So how do we train this model? So the learning is actually driven by an autoregressive loss that's trying to penalize for long-term error. So remember, this model is predicting a sequence autoregressively. So we can actually get an error at every step in this sequence. So that is our autoregressive loss. And to train this model, we are using a supervised way to train it. We have our data set, which is 40 years of historical weather forecast. And this data set is called ERA 5, and it's released by ECMWF. It's a data set that you can acquire as long as you have the license from them. And we do a causal split on this data set so that we do not have information from the future. For example, like during the model training, we will never know what's the weather gonna be like, what's the trend gonna be like in 2018, if it's gonna be too hot or too cold. Yeah, so this way we can be sure that the model can actually generalize well to future years. Cool. Next up, we're going to show some evaluation results. So here we're showing an ECMWF style scorecard. So what is this scorecard? This is some visualization tool developed by ECMWF. And it comes in handy because in weather forecasting, we have so many variables that we need to compare to. So how do we read the scorecard? So basically the x-axis here, these are the lead times from 6 hours up to 10 days. And the y-axis here are the variables at different pressure levels. So for example, the T here stands for temperature. And it has so many different pressure levels because we're measuring the temperature at different levels of the atmosphere. And looking at this graph, the blue part means that GraphCast is better, and the red part means that HRAS is better. And the darker the blue is, GraphCast is better in that case. So you might have noticed that there are several red lines here. So if you look closely at the scorecard, these red lines pretty much only occurs when the pressure level is at 50. So what does that mean? So pressure level 50 is actually the stratosphere, which is pretty much on top of the atmosphere where you're almost going out to the outer space. So this part actually matters less for human activities, and that's why weather agencies generally care less about it. So if we take away all of the variables that are in the stratosphere and measure everything else, GraphCast is actually better than HRAS by more than 99% of all of the targets below the stratosphere. Cool, so now we know that we are performing better than HRAS on most of the targets, but how much better are we comparing to HRAS? So that's why we show this graph here. So here we are only showing 4 variables. One is geopotential, one is specific humidity. These are pressure level variables. And we also show surface temperature and surface east to west wind. So these 4 variables are just representative, and the trend also holds for all of the variables that we're predicting. And you should be able to find the full plot in our paper. So how do we read this graph? The first line here shows the absolute performance, and the absolute performance is measured by the rooted mean square error when we compare to the ground truth. And the x-axis here is the lead time from 6 hours up to 10 days. And the black line here is HRAS, blue line here is GraphCast. So you can see here that for all these variables, GraphCast is better than HRAS. But still, it's not quite clear like how much better exactly that we are, like in what kind of percentage. So that's why we show the second line, which is the relative performance, which is a normalized RMSE difference. And we are normalizing it against the black line, which is HRAS. That's why the black lines here are all at 0.0. And we can see that for the blue line here, pretty much all of the time we're like 10% lower than HRAS. Yeah, meaning that GraphCast is better than HRAS by 10% mostly. Cool, so now we see all the evaluation results, and let's dive deeper into some downstream applications that we are looking at. So one of the applications that we're looking at is hurricane tracking. So the goal for hurricane tracking is that we want to predict the center of the hurricane accurately and also early in time. The reason we want it to be early is that we want to give time for the public and the government to prepare for a hurricane if it's going to arrive anyways. So here we show an example, which is a Hurricane Maria. It's the worst storm to ever hit Dominica, St. Croix, and Puerto Rico. And it caused close to $100 billion in damage. It's the 3rd costliest storm on record. And here we show a comparison of the 2 models' prediction on this hurricane. And on the left, we have HRES, and this black line here is the actual hurricane path. So the black lines are the same on both graphs. And the red lines here is the predicted hurricane path from this model. So we can see here that HRES is actually making a huge mistake. It thinks that the storm is never going to hit the coast. However, it actually hit the coast and caused a lot of damage. However, in GraphCast, you can see that we avoided this error, and also the error in terms of distance is also much, much smaller. And here on the right, we show some aggregated information for all of the hurricanes we look at from 2018 to 2021. Here again, x-axis is the lead time, and y-axis is basically the error in terms of difference, which is in kilometers. So one major takeaway from this graph is that we perform better at longer lead times. And at longer lead times, we can achieve like a 9-hour improvement over HRES in terms of predicting hurricane centers. And the next application that we're showing is predicting atmospheric rivers. So what are atmospheric rivers? These are called the so-called rivers in the sky that are transporting water vapor away from the tropical areas and dump it onto the continents. I don't know if there are people from the Bay Area or California here. We've experienced some of the worst storms this past winter and this past spring. So these are all brought by the atmospheric rivers. There were 12 of these rivers hitting California in the last spring. So it's really important. It's really important that we predict these rivers accurately and also early in time. So here we show a graph of the relative performance of HRES comparing to GraphCast. And we can see again that we are performing better at longer lead times. And also generally at longer lead times, we can get like a 1-day improvement in terms of accuracy. So because of all these abilities that GraphCast has attained, and also remember these abilities are attained by even without training on these hurricane tracking or atmospheric river tasks. So it's solely because of GraphCast has a better ability in predicting weather forecasts. So we are planning to take GraphCast out of the lab so that it can benefit all of the downstream sustainability projects in Alphabet that are relying on accurate weather forecasting. So here we show an example of our productization engagements, which is with the flood forecasting team inside Google. So every year, floods can cause up to 60K fatalities and cause more than $33 billion in terms of damage. And skillful weather forecasting is the #1 most impactful improvements to its overall accuracy. And remember, GraphCast is really good at hurricane tracking and atmospheric river forecasting. So these abilities give us some confidence that it will be able to help with the flood forecasting task. So how does the flood forecasting inside the Google, how does the team's model work is that they have a hydrological model that is taking in weather data, and then they're gonna feed the result of the hydrological model into an inundation model to see if the water is actually going to flood. And then they have a mechanism to distribute all of the warnings to consumers and also to governments. So the way that we are going to help is by simply, we can feed the GraphCast forecast into this hydrological model so we can perform along with all of the other weather data that they are already acquiring. However, there are also challenges in putting this into production. It's not like a plug and play work. For example, some of the efforts that we are looking at include increasing the time granularity of our forecasts. So before our forecasts are at a 6-hour step, but for more accurate flood forecasting, we probably will need a 1-hour step forecast. So yeah, these are some of the challenges that the team is working through towards this productization effort. Cool, so yeah, if this was an interesting material to you, you can check out our paper and our GitHub. So last week, we just finished open sourcing our code and pre-trained model on GitHub, and you can access them on the link here. So in this GitHub repo, we include a Colab notebook, which is a notebook that you can open and load our pre-trained models, and you can play around with all of the historical forecasts that we're generating. And also all of the materials that I introduced here are also on our paper on arXiv, and you can read more on arXiv. And if you have any questions and have any suggestions to our work, you're welcome to send email to this email address. Cool. And lastly, we're hiring. So if you're interested in our positions, do go on our website to check out our careers page. Currently, we have open positions in both London and Mountain View. And personally, I am a research engineer sitting in Mountain View. So if you have any questions about the role or about the work, you can reach out to me. My name is Flora, and this is my email address on top of there. Cool. Thank you.